talk about today are fuzzy axionic dark matter, and that's going to be exploiting a macroscopic quantum gyroscope. I say quantum in the sense that it's based on electron spin. Quantum is purely a quantum thing. And then a Fourier-Bessel short distance test of the gravitational inverse square law. This is our group. Unfortunately, two very important people were not in this picture, PI and Blaine Heckel. They weren't there at the time the picture was taken. So direct detection of particle dark matter, this again has been pointed out. The WIMP miracle is no longer so miraculous, and attention has now turned to the possibility that the dark matter is bosonic, and that recently the idea that it's such a light particle that it behaves as a wave, as was pointed out, and the effect on a spin moving with respect to this wave can be described by this effective Hamiltonian here. And I'm going to assume that this wave is perfectly coherent for the time being. It may or may not be true, and it also it may or may not be true that the effective density is what the average dark matter density is. So what should we expect for the magnitude and direction of this velocity? There's a simple isothermal isotropic equilibrium model, and that's very simple, very easy to calculate, but it is not realistic because we now have evidence that there are dark matter debris streams that have to do with mergers, and a significant fraction of the dark matter is in such streams. And if the solar system were to lie in such a stream, the velocity of the axion could point in any direction and with a magnitude that just has to be less than the local escape velocity. So we're taking an agnostic position. We say we don't know what the direction of the dark matter wind is, but we do know that its velocity can't exceed this few hundred kilometers a second. Now, this test is based on a quantum gyroscope. This is a object about the size of my fist that has net spin, net angular momentum, and it really is a gyroscope. I mean, it behaves in every way like a gyroscope. No moving parts, but it is a gyroscope, okay? And it's possible because it's basically a sophisticated permanent magnet made of two different materials. One of the materials, all the magnetization comes from electron spins. It's a magnet iron, if you like. And the other permanent magnet is samarium cobalt. And this is kind of a remarkable thing because the cobalt, the samarium in this samarium cobalt is in a 3+ ionic state. Its spin points along the total magnetic field, but the spin B field, the magnetic field from the spins, is nearly canceled by the orbital B field that's in the samarium cobalt. And so the spin in this samarium cobalt is almost, the magnetization in the samarium cobalt comes almost entirely from the cobalt. The samarium has effectively a very tiny magnetic moment, okay? And you set it up so that the magnetization is uniform in this puck, as we call it, and that satisfies Maxwell's equations. And if you just work out assume the G factor for spin is 2, then the total angular momentum of this object here is the negative of the spin, okay? And it's actually pretty easy to see why this works, okay? But you notice we've set these pucks up so that the magnetic field runs around this way, over here, the other way, that way, and it's got the symmetry so there's no net, composition asymmetry in this thing. There's no net direction of the B field inside. okay? And the center of the spin distribution is the center of the pendulum. So it's got some nice properties. It's interesting to see, very easy to see, I should say, how this arises, how the samarium cobalt can do this, okay? Are you familiar with Hund's rule? You're AMO, right? Hund's rule tells you how how the electrons are distributed in an atom, right? The spin function has to be maximally symmetric to keep the space wave function maximally antisymmetric because electrons repel each other. And then there's a rule about at the beginning of the shell, the two things point. Anyway, Hund's rule would tell you that samarium in the 3+ ionic state has 0 magnetic moment if you were to do it, okay? And so when we combine these things, we have net angular momentum, net spin, and it's a static thing, okay? And here it is. You see this is my hand. It's a very small little object. It's attached through a thin torsion fiber. Somehow this is not shown. And these mirrors we use to detect the twist angle of the thing. And this sits on a rotating torsion balance. This is an ancient instrument, but we've been taking data for a long time with this spin pendulum. And if you look at the power spectrum of the pendulum twist angle in the rotating frame, okay, this is the frequency here is 1 times the turntable frequency, 2 times, 3 times. And this blue curve, the area under that is KT. So this thing is really, we're seeing the, the Brownian motion of this 70-gram thing. The science signal is right here. There is a signal here, and that's because the turntable isn't absolutely perfect, okay? And so you have to get rid of that fake effect. One way to do it is to simply rotate the pendulum 180 degrees in the turntable frame, and then that phase reverses. Or you can use the orientation, the astronomically modulated signal from the Earth turning around every 24 sidereal hours. And what we do to analyze the data is we look, does the spin prefer to lie in a fixed direction in the lab, okay? So the turntable is turning around, and if there is a fixed direction in the lab, we look for a torque that varies sinusoidally as this thing turns around. Thank you very much.
Button on top.
Great, thank you. Okay, so we're looking for a signal as the turntable turns around that, goes like the cosine of this angle. And then now, furthermore, we say now this thing isn't actually steady in the lab. It's modulated at the sidereal frequency and modulated also by the possible Compton frequency of the axionic field that we're looking for. So this is a gyroscope in every sense of the word, okay? The total spin points south, not north like a gyroscope does, but that's because the J was the negative of S, okay? So this is finding north, if you like it. And it finds north with a very good accuracy. So this is the signal going east, this is the signal going north, and right up there is our measured point. So this thing really points north. It is a gyroscope in every sense of the word. And it's sensitive enough that we could set a limit on, is there a direction fixed in the universe that a spin likes to lie? And if so, what is the, if not, what is the upper limit we can say is the energy difference between a spin lying in that preferred direction and opposite, okay? And that's this very tiny number, which is comparable to the electrostatic energy of 2 electrons separated by 90 AU, okay? So it's a very sensitive little gizmo. And so we took used this thing for a number of different experiments before we ever knew about the fuzzy dark matter area. We've done a bunch of other experiments listed here, and these show the measurements. We say the energy of the pendulum is proportional to this, and these are the coefficients for this beta. Okay, and you see the data span a very long time. The error bars are not the same for every data point, every data set. There are gaps in it. Okay, and the way we analyze this is in each one of these data points here, we've taken 2 complete turntable revolutions and looked for something that varied at the turntable rotation frequency. I make a pitch here for analyzing things not using Fourier transforms, which is apparently the normal way AMO people think about how to analyze things. The right way to do it is to do a linear least squares analysis. You make no assumptions that the points are equally spaced, that all points are equally weighted, etc. Okay? All the physics is put into a linear term that multiplies, all of the rotations, the Compton frequency, everything like that. So you're looking for linear coefficients, okay? And the signal you're looking for is modulated by the turntable angle, modulated by the Earth's sidereal rotation, and modulated by the axion's Compton frequency. And the signals in the galactic, in the celestial equator plane are triply modulated. The signals along perpendicular are only doubly modulated. And they are difficult for us in this experiment to distinguish from lab fixed effects. And so for the moment, we don't consider them further. Okay. So what we do is we compute 8 basis states, I call them, at each assumed axion frequency for each measurement, where these basis states have something to do with the transformation between local and celestial coordinates, a term cosine and sine of the Compton frequency, and then a term here which has to do with the attenuation of the signal if its frequency is, high compared to 1 over the length of a data point. Okay. And so we get a whole collection of these things, and then we do a scan over a whole bunch of possible axions frequencies, make this linear fit. Okay, so we get these coefficients here and here, and then we don't know what the phase of the signal is. We're trying to see a signal with a frequency we don't know and a phase we don't know. The frequency we've taken care of here, so we want to marginalize over the phase. And the way you do that is by taking the square of the cosine quadrature and the sine quadrature, and do the same over there. Okay? And the important thing is we're fitting these 2 quadrature components simultaneously. If you fit for one and then you fit for the other, you're going to get the wrong answer. You're not going to find out the correlation between these, which is a very important thing. Now, something happens when the Compton frequency coincides with the sidereal frequency, okay? Because then these terms, these 8 terms are not all independent, okay? They drop down to 4 terms, okay? And some of these basis states lose power at this particular frequency, okay? Because our basis states look like sine of one frequency times cosine of another. If those 2 frequencies are the same, okay, now you're going to get something that looks like, for example, 1 plus cosine of 2. And we throw the 1 away. We throw away a constant term because that looks like a laboratory fixed signal, which we cannot assure you vanishes. Okay? We can't assure you that a laboratory signal vanishes. Okay? And so the power of these basis states has a little funny behavior. Whoops. I thought I had that slide that showed that. Well, what's going on here? This thing's frozen. Does anybody have a clue what's going on here? Oh, now, let's see if now it goes. Okay, well. So at any rate, here's what you see when you look at those fit coefficients, the 67,000 fit coefficients. Okay. For example, the X cosine signal is a nice Gaussian. The X sine coefficient is a nice Gaussian. Mean zero, the same width. Okay. If you make a similar plot where now you plot the number of amplitudes divided by the uncertainty of the amplitudes, this is Gaussian with the width, which is basically 1. That says the errors input errors on the amplitudes were reasonable. And then when you marginalize, you turn the Gaussian distribution into what's called a Rayleigh distribution. The Rayleigh distribution is the two-dimensional version of the Maxwell-Boltzmann distribution, if you like, okay? Oh, yeah. Huh?
Could you just do it full screen?
Yeah, okay, here. It went away before, so I'll put it back here. Something is going wrong here. Good, okay. So here is a stretch of data analyzed as a function of frequency between 10 to the minus 8 hertz and 10 to the minus 4 hertz. And this orangey color, I'm colorblind, so I may call these the wrong thing, okay, are the data. And then here, this blue term, we took our data and we added to the signals in the raw data a signal corresponding to a 2 zepto-electron volt, 1 microhertz cosine signal. And you see there it is, it's resolved at 17 sigma. And this structure here is what the linear least squares analysis tells us is the result of the unequal spacing of the data and the gaps and everything like. Everything comes through. Okay? This plot here shows the power in the basis states. And this is the point when the sidereal and the Compton frequencies coincide. And this fall off here has to do with the fact when the signal gets a high enough frequency, bigger than the inverse of a datum, starts to average a signal away. I don't want to go over this, but if you actually look at the errors, if you're looking for a signal and you want to do the conventional thing of, that you would do for a Gaussian distribution in one dimension, you would take mu plus 2 sigma. In the case of a two-dimensional thing, the analogy of that is called a Rice distribution, and we do all of that properly. And the constraints are shown here. And the simple, unrealistic halo model is shown right here. And these are the agnostic model, where we say we don't know whether we lie in a stream or not. We think that's a better way to analyze things because it allows you to use that data if you have a different picture of what's going on. Now, we've been involved in a dispute. And I want to take a moment to talk about this. the low frequency limit, FA equals goes towards 0, is not the same thing as looking for a DC effect. Okay? For looking for a DC effect, in our way of looking at it, you would fit one coefficient, the cosine, let's say. Okay? It would be just one. I mean, if you're looking for a signal whose phase you don't know, you need to fit two quadrature coefficients. Okay? Or another way to say it, if you claim you are setting a limit on something with a very low frequency, that's not the same thing as setting a limit at DC, because when you say I've said there was a signal, I could detect a signal at this low frequency, that means you had to have been able to tell that something was changing at that frequency. Okay? It's an important point. Okay? And here is an example where people didn't really get this right. This Kasper-Zulf experiment, which is a lovely experiment. I have no beef with the experiment. It's a great idea. It's a lovely experiment. My beef is in the analysis. Okay? Here is where the signal should start going 1 over f. Okay? Because if you think about it in the way we do, one of your coefficients is going to go like sine omega t and the other like cosine omega t. When omega t gets to be a small number, that sine coefficient gets very small. And therefore, when you ask what's the constraint on it, the constraint gets very weak. And so this thing has to go up like 1 over f. And you look, this is another experiment here. It roughly did that. These people said the constraint actually got better. Okay? It can't. Okay? It just can't. And I'm beating a horse here because it's still persistent. This is a paper from August. We've been telling people that this isn't right for a long time. And yet, you know, what this should turn into is a slope of 1 over f. So I'm taking this opportunity for a paid advertisement for our point of view. I also recommend that experimenters making searches like this should always include their results marginalized over the phase, but not over different halo models or coherence models or anything. So all experiments, you can put in later what you want for your model. Okay, that's your choice. But you should marginalize over the phase because you do not know it. Switching gears. Thanks. Giorgio explained this slide and showed that picture. He's made this point already. The force is very weak. We'll see just a few slides later. The alignment's tricky in our case. We have, 6 centimeter or 5.5 centimeter size objects, one of them hanging from an 83 centimeter fiber, and we have to align it with something which is, tens of microns away, that is not hanging from the fiber. It's, major alignment issues. Unshielded backgrounds are enormous. You need a rigid conducting foil between the source and the pendulum. And I'm very glad that, to see Giorgio's very nice rigid thing. Okay. It's important that it's rigid because the Casimir force or electrostatic potential differences could deform the foil, and then it isn't working right. And cleanliness, of course, is very important. And our latest instrument has what we call Fourier-Bessel geometry. It's a cylindrically symmetric object, and it's got various azimuthal symmetries. This is 120-fold azimuthal symmetry. That's 18-fold azimuthal symmetry. This geometry, if you have two identical ones, one rotating under the other, you can predict the torques with only one numerical interval. All the rest is analytic. Okay, and not only can you predict the torques for Newton, you can predict them for Yukawa, and interestingly enough, also for the dipole-dipole interaction. Okay, and you'll see why that's important. Okay. And this geometry where you have 50% transparency in both of these patterns is optimally efficient for the signal strength. It's maximized, and so any little deviations from it don't matter. So it's actually a very sweet geometry. And this shows the first version of the experiment done by Ted Cook. And you see here is this tightly stretched foil. The attractor has been glued to the bottom of this torsion pendulum. There are three little spheres here. We use those three little spheres to make an absolute calibration of the torque scale by rotating three big spheres outside the vacuum vessel on its own turntable. And this shows, again, the nice property of the Fourier vessel expansion. The 120 omega is the 120 times the rotation frequency of the turntable. Signal drops exponentially with a steep slope, and the 18 omega signal drops with a much less steep slope, and a Yukawa signal drops with its own exponential form with an even steeper slope. So that it's beautiful because you can analytically solve a lot of it. And this is a simulation that Ted made of what you would see, or what he sees, as the turntable rotates, speeded up by a factor of 1,000. Okay, and you see this is the signal from the 120 pattern, and this modulation is the signal from the 18. So what you're doing is you're basically testing each data point at each separation is testing the inverse square law at two scales at once. And this shows you what Ted saw at two different separations. And the interesting thing here is that these two sets of masses, the one in the attractor and the 18-fold in the attractor and the 18-fold in the detector, were each 200 milligrams. Okay, this is by far the smallest set of masses for which gravity was ever observed, and it's resolved at 50 sigma. Okay. Well, we didn't publish Ted's work because there was a small flaw in the attractor, and we thought we had discovered some evidence that there were maybe some magnetic effects that we didn't understand. And we discovered that the shop, not to our knowledge, had sandwiched the stack of these tungsten foils between two stainless steel shims when they were EDMing it, okay? And so we thought, oh my gosh, we don't know for sure exactly, that we didn't have all the systematics well under control. And so we decided to mount a second generation experiment. It was hard to do much better than Ted, but here we replaced the tungsten pattern. We carved instead the pattern out of platinum, which is a softer material and easier to keep flat. We have to glue it to something to support it. It's a very flimsy thing. So they're glued to glass annuli. Okay? And this shows a picture of one of the test bodies glued to the glass annulus. Okay, the glue in this case fills the holes. Okay, and then we gold coat it, and here's the gold coated thing here. Okay, and if you look very carefully here, you can see little hints that you can see a little bit of that pattern in there. That was very important that you could see a little hint under the microscope. Okay, because that's how we could be sure where the center of that pattern was with respect to the turntable axis. Okay, because when you glue it down, you don't know within microns where the center is. Okay. So the new experiment, which is John Lee's thesis project, we have platinum instead of tungsten test bodies. We fabricated them by a different gluing technique. Very importantly, we put this isolation foil here, which is, again, different than it was, on 3 actuators so we could remotely position this. So we're moving these things around by microns, okay, and trying to get the alignment just right. And the point, this slide is, I'm trying to make 2 points. One is that we make the gravitational calibration with the spheres on the external turntable throughout the time that this 85 days which data were taken. So you can think of this experiment really, because the length scale here was like 10 centimeters separation between the test bodies. That's about the separation where Newton's constant is always measured, okay? So we know, and inverse square law has been tested very well, 10 to the minus 3 level at that length scale. So our experiment can be viewed as measuring Newton's constant at a bunch of separations down to 50 microns, okay? With good resolution, okay? But, you know, the absolute accuracy is nowhere near what the 10 to the minus 5 or better of Newton's constant at the big distances. Okay. We arranged the turntable rotation frequency. This is the signal from the 18-fold pattern. This is the signal from the 120-fold pattern. And this is the third harmonic of this 18 signal. This peak happens to lie at the second harmonic, but it has nothing to do with the second harmonic because there is no second harmonic. The symmetry of the pattern says it's got to be 1, 3, 5 harmonic. This is a residue of the free torsional oscillation. Key thing is knowing what's the separation between the center of the pattern on the detector and the center of the pattern on the attractor. Okay? And the way we determine the horizontal centering is by looking at the gravitational 120 omega torque as you displace the XY Z stage horizontally. Okay? And the maximum is when the two centers are aligned in the horizontal plane. Okay? And all these points, if you don't see an error bar, they're smaller than the data points. Okay? And these resolve the horizontal displacement between these things, right, which are 5.5 centimeters in size to 2 microns. Okay? And the vertical separations, we measure the electrical capacity between the pendulum and the attractor foil, and between the attractor foil and the between the pendulum and the isolation foil, and between the isolation foil and the attractor. And also measure the thickness of the foil and so on, and that gives us the vertical separation. We discovered an interesting thing at the end of the experiment. We did all our usual tests, and then we imposed external magnetic fields. And we found that if we had a vertical magnetic field, as a function of B field at a fixed separation, there's this parabola here. That's the magnetic torque. Okay, it's due to the fact that the magnetic susceptibility of the platinum causes the platinum to slightly polarize in a field which is or the Earth's field. Okay, and that spin-spin interaction between the spins in the attractor and in the pendulum gives you this torque, which fortunately we can calculate with the Fourier-Bessel expansion. Okay, and so what we measure is this parabola. This is the point at which the magnetic field is 0, because this is the value we measured during our science data here. Okay, so at this point, this is when the field at the detector is 0, and that happens to be just what it takes to cancel the field we measured, which is roughly the Earth's magnetic field, but it's bolted to a big old cyclotron magnet, so it's not exactly the Earth's field. Okay, and then we studied this, or John did all this now, as a function of separation for a fixed applied field. Okay, and this is the Fourier-Bessel calculation of that. So it really agrees. Everything makes sense, and this shape is very nearly identical to what the gravitational torque is. For all practical purposes, it's identical, but it's only appreciable for the 120 omega signal. For the other two frequencies, the magnetic effect is very small. And that, there's John. There is Helmholtz coil, the little spheres for his calibration turntable, looking very proud because he's about to be ready to write his thesis. And one last thing is, these kind of experiments are interesting because key properties of the instrument you can't learn as well by external measurements as you can simply by studying gravity. So what we do is we measure the masses of the materials, of the test bodies, by saying how much material did we cut out, weight of the material we cut out to make them, okay? And we use these capacitance measurements to get the vertical component of separation. The thicknesses of the materials we measure with, mechanical means. The density of the glue John measured, but he only measures it within a certain accuracy and so on. At any rate, what we do is we allow some of the key instrumental parameters that we can measure externally to add to our chi-squared. Okay? And so that means that we are including the systematic errors due to the uncertainty in these particular things in our fit. Okay? It's actually a very useful thing because in the past it told us interesting things. At one point, we thought we had discovered a weird effect because we were measuring the system with 21-fold azimuthal symmetry and measured the 42 signal, the harmonic in that case, which wasn't at an optimum level, so there was a second harmonic. And it didn't agree with what we'd measured with the fancy coordinate measuring machine that was bought with Sloan survey money to, locate the little places where they put the fibers in to find the galaxies. And it turned out it was because the measuring machine was wrong, because the measuring machine had a little tiny ball that it moved around, and the ball rides over the high spots on a surface roughness. Gravity knows about the gaps in the surface roughness. So that's an example of how, if we didn't allow these parameters to be constrained in this way, we wouldn't be getting as useful information. So this shows the torques that are measured. Okay, there's 271 chi-square for 285 degrees of freedom. Here's the torque scale. There's 1 femtonewton meter. That's 1/10 the weight of one E. coli placed at the end of a massless lever arm 1 meter long. Okay, so this is really a very tiny force. Okay, and then I show you here the Newton fit. If you then say we will look for an additional Yukawa term, a single additional Yukawa term, okay. We add that and redo the chi-squared fit. At every point, we let the instrumental parameters float within their measured bounds. Okay, so we're not requiring them to be what Newton told us. We say whatever gives you the best fit. The best fit gives you a lower chi-squared by 3.3. The 2 sigma limit on chi-squared in 2 dimensions is 6.2. So this is not a significant result at 2 sigma level. It happens for a force with a range of 8.9 microns. Okay, and this shows the new result. It doesn't look so much better, but there's an order of magnitude or more in this vertical direction here. Some implications of the result, we can say the dilaton must have a mass greater than 4.9 millieV. The largest single extra dimension must have a radius less than 31 microns. And these are easily the best constraints on those things. So thank you for your attention. I'm very interested to hear all the marvelous progress that all the other people here are talking about. It's a great workshop.
Going back to the beginning part of your talk, you described the electron spin as a gyroscope, and you showed gyro compass data. And
I mean, our gyroscope compass data.
Your gyro compass state.
Yeah, right.
And I went by quickly, but the units were, you resolved nanoradians? Was that?
No, okay. The units there were the, let's see if I can quickly go back to that. Those were the twist, the signals, the twist angle signals. It's not resolved at nanoradians. Sorry. There. Okay. These are the twist angle of the pendulum corresponding to a torque in the east direction, and these are the twist angle of the pendulum corresponding to torque in the north direction. So you have to multiply this by the spring constant of the fiber and stuff like that. And that would give you a torque. Okay, so if you want to think about it, these are really just proportional to the torque in these two directions, okay? And, you know, there's a little bit of technology here. The points, there's a little circle up here. Whoops, the wrong one. That little circle is, if we use the gyrocompass effect to calibrate the number of polarized spins in the object, okay? This band here, it really should be an ellipse, you know, with the same width as that thing, is if you took what people knew about the magnetic properties of samarium cobalt 5, you know, from experiments with polarized neutron scattering or circularly polarized synchrotron radiation and so on. Okay, so we've actually determined the spin properties of samarium cobalt 5 better than the solid state guys, but you know, you can see how accurate it is. It's nowhere near nanoradians, right? I mean, this is a spread here, you know, degree or so. I mean, it's not, I'm glad you asked, because I didn't want you to think I had measured that. No, you were right to be.
Questions. First thing is, so again, in this experiment here, I'm always amazed by the, so you have to cancel the magnetic moment.
Yes.
In some decent, how well do you cancel the magnetic moment?
Okay. I don't have it in units of magnetic moment, but I can tell you, you know, if when you assemble this octagon, okay, at the joints there, they're not perfect. It's pretty hard for the machinist, because this thing is, the samarium coil is so magnetic that, you know, it's easy to get a little tiny ding in the sharp edges there. Yeah. And so a little bit of flux pops out at those things, okay? But then it sits inside the magnetic shield that's shown there, and when you do that, and then the instrument itself, the rotating instrument, has magnetic shields around it, then it's phenomenal. You get this limit that I told you about.
I'm always amazed how that you can do something like that. I was trying to put some numbers.
Yeah, I don't have the number for the magnetic moment. That's, I mean, I'd like to give it to you, but you know, you can appreciate, for instance, you know, we had these objects with test bodies with in that other second experiment I talked about, with, you know, masses on the order of gram, and the induced magnetic field in the platinum due to the Earth's field, you know, was trivially measurable. Okay, so the sensitivity is not an issue for us, and you never know when you start this how well you could do. I never knew, and one of the greatest, most pleasant surprises I've ever had in my professional life is finding out how well, in fact, it works, okay? But it does. But, you know, the time scale for these experiments is not an AMO time scale. I'm impressed how fast clock people are advancing and all of that, and you're advancing and so on. You know, this went on for several years, learning how to do this. And that was the third pendulum we built, you know, of this spin kind, okay? You build the first one, you find out what you could do better, and so on. So
Okay, so the other question was, is there a preprint on the gravity measurement?
is there what?
A preprint or some sort of...
A preprint?
Yeah. Or
Basically, I've got a version right now. I'm going through the rest of the authors, but I'm happy to show it to you. But we'll send it off to archive, in weeks. Yeah.
Okay.
Yes, Dave.
So when you do that fit for the short distance, do you put in any patch potential terms or any background if it's all internal? And how, but you're allowing the mass densities to float a little, did I understand that?
Okay. So what we have is the important parameters really are the separation. Where at what micrometer settings would everything touch? Okay, and the horizontal is less important. And then the masses and thicknesses of the test bodies that we've glued up. And then there's a small correction for how much glue is in there, okay? We let those things vary within the degree to which we can measure them externally. And, we could get a better result if we said, look, we have a beautiful Newtonian fit, and now we will just fix the instrumental parameters at the Newtonian value and then add a Yukawa. But that's the kind of swindle that...
But at the measured best values, your residuals are consistent with Newtonian.
Yeah, yes. And at that Yukawa, they're also still consistent with our measured best values. So the measured best values they're distributed. The errors that we assigned are, externally are consistent with the contribution to chi-squareds they make. But it's an unusual thing, but this is an unusual circumstance. Normally you know your instrument very well compared to what you're looking for, and so it's not something, that's given as one of God's numbers, and you just, but if you do that, you're not being really fair, because gravity has told you about those. I gave you that one example. There's several. The first time this came, it turned out that we had, before we did this procedure, we had a XYZ stage where the X and Y were one kind of micrometer and the Z was another one. And it turned out that it was, some optics company that made the Z micrometer, and it wasn't actually scaled right. It was off by a number which could have been 1.024. I mean, consistent with it. Like they had, 2 to the 10th is 1,000. Okay? And we found that out the hard way. Okay? And so it's important to have some freedom within the accuracy. In that case, we hadn't measured it. Okay? If we'd have measured it ahead of time, but we just said, look, it's got a stepper motor and so many turns per inch on the thread, we'll believe them, okay? But you couldn't. And so that's when we started thinking, okay, we better take, and then when we found the second harmonic of the 42 signal disagreed with what this big fancy coordinate measuring machine told us, that really said, look, you've got to only put the instrument parameters in as hard numbers to the degree to which you know them as hard numbers.
So, we're out of time, so thank you very much.